friends. So we're going to look today at doing inference on a difference in means. So we're going to start here with a confidence interval, and then we'll look at a significance test in the next video. So we're going to take this chocolate chips problem. You have this worksheet. We're going to start like we do in reading and pulling out important information. So this says that Ashton and Olivia want to know if generic chocolate chips have as many chocolate chips as name brands. So do generic have as many, right, chocolate chips as name brands? So to investigate, they randomly selected 10 bags of Chips Ahoy cookies and 10 bags of Great Value cookies, which you get from Walmart, by the way, and randomly selected one cookie from each bag, and then carefully broke apart each cookie and counted the number of chocolate chips in each. So my variable X is the number, the count of chocolate chips in a cookie. And here I have two populations. I have population 1 is all Chips Ahoy cookies. And from that, N1 is 10. So we had 10 cookies, one from each bag selected. And this is my data, right, for those. So this would be X1, this is X2 from each cookie. Population 2 is all Great Value chocolate chip cookies. And from that, we also have a sample of 10 bags from each. We took a cookie and counted the number of chocolate chips. So I guess we have this here. So we're going to let CA be Chips Ahoy chocolate cookies. N is 10. Right? And for Great Value, N is also 10. And we would like to know the mean and standard deviation. So I have in my calculator already entered this data as list 1 and list 2, and I would like to know the mean and standard deviation. So if we go back into stat and calculate, let's do two variable stats. We can get this information other ways, but this will work. So we want to do two variable stats on the information that's in list 1 and in list 2. We'll leave the frequency list alone and we'll calculate, and it tells us that X bar, that's our first variable, is 18.4. So that's the mean number of chocolate chips from the 10 Chips Ahoy cookie. And scrolling down, S sub X is 1.776. So I'm going to call that 1.78. If I continue down, I have a Y bar, which is 19.4. That's the mean number of chocolate chips for my Great Value cookies. And the standard deviation for that is at the bottom of the screen, which is 3.59. We'll round that to 3.60. So I have the mean, the sample mean, and the sample standard deviation from each set of cookies. So we want to construct and interpret a 99% confidence interval, right? This is our confidence level, for the difference in the true mean number of chocolate chips in Chip Ahoy and Great Values. So in our state, we want to estimate the difference between the means of our two populations. So we often use mean 1 minus mean 2. This is using letters. So we'll do mean of the Chips Ahoy cookies minus mean of the Great Value. Right? And for our calculator, that's going to be mu1 minus mu2 at the 99% confidence level, where mu of CA is the true mean number of chocolate chips and Chips Ahoy cookies, and mu GV is the true mean number of chocolate chips and Great Value cookies. Our plan is that we are going to calculate a two sample, right? Two samples, one from each of two populations. For mean, we will typically use a t-interval, right? Unless we know the population standard deviation, which we don't. A t-interval for our difference in means. Right? And those are population means, not sample means. If our conditions are met, for a mean, we have our random condition, and the data come from two random samples.
Good morning.
From two random samples of bags of cookies Our 10% condition would be that 10 is less than or equal to 1/10 of all Chips Ahoy bags, and that 10 is less than or equal to 1/10 of all Great Value bags, and that would be certainly true. Our normal large sample, right? Remember, for mean, we either look that the population distribution is normal, and we don't know what the population distribution is here, or that we have large samples. And by large samples, we are looking for those sample sizes to be greater than or equal to 30. In our case, both our samples are small. They're both less than 30, right? So we're going to have to look at the graphs of the distributions. So if we come in here and we graph our Chips Ahoy, we're going to do a dot plot. We had 17 chocolate chips in one cookie. We had 19. We had 21. We had 16. We had another bag with 17. We had one with 18. We had one with 20. Another one with 21. Another one with 17, and then another one with 18. So in this distribution, there is no strong skew or outliers. Looking at our Great Value distribution, we had one cookie with 22 chocolate chips, one with 20, one with 14, one with 17, one with 21, another one with 22, one with 15, one with 19, one with 26, and one with 18. Right? So a bigger spread on that one, but again, there's no strong skew or obvious outliers. Right? We might question this, but it's not way out of the pattern of the rest of the ones. So we'll go with that. So because we don't see that strong skew or outliers, we will proceed with some caution. So when we do inference about a mean using a t-distribution, we need degrees of freedom. And for two samples, your degrees of freedom will be the lesser of n1 minus 1 and n2 minus 1. Right? Since both samples were of size 10, right, then we've got 10 minus 1 in both cases. Those both equal 9. Right? So one is not smaller than the other. We will use a degrees of freedom of 9. But if we had a sample of 10 and we had a sample of 15, we would take 10 minus 1, 9 as our degrees of freedom because it is the smaller of the two. Our critical value for 99% right? And we can get this from our T table, right? Is that your T star for degrees of freedom of 9 and 99% is 3.250. So our confidence interval will be mean 1 minus mean 2, which for us is going to be 18.4 minus 19.4, plus or minus our T star, which is 3.250, times the standard deviation of our sampling distribution, which for means is going to be our standard deviation from our first sample, which is 1.78 squared, over that sample size, right, this is N1, which is 10, plus the standard deviation from our second sample, which was 3.60 squared, over its sample size, which is 10. Remember, when we square our standard deviations, we're getting our variances. Variances add, standard deviations don't. So we simplify those, and 18.4 minus 19.4 is -1. Right? So that difference being -1 gives us some evidence that, that the number of chocolate chips in Chip Ahoy is less than that in great value. But is it significant evidence? Well, that's what we're getting ready to find out. So we multiply these two together, which give us our margin of error, and that ends up being 4.127. So subtracting and adding that from 1, we get -5.13 to 3.13. By calculator, we would do a 2-sample T interval, right? 2-sample T interval, where it will ask us for information, and we're going to take this from data, where that data is coming from list 1, which is our Chips Ahoy data, and then list 2, which is our great value data, and then we need a C level, which is 0.99, and then it asks this question, pooled. And the answer to pooled is always no. Okay, do not pool. When we did difference in proportions, we combined our 2 samples into one, but we do not pool. So just don't worry about what it means. We don't do it. So here we go. We're going to go into our calculator now. Shows up. And we're going to do a test. So we're going to do a 2-sample. Okay, we're going to do a 2-sample T interval from our data, where our data is in list 1 and list 2, frequencies of 1 with a C level of 0.99, and again, we are not going to pool. We're going to come down and calculate, and we're given our interval. We're given a more specific degrees of freedom than we estimate with 10 minus 1, and we're given information. So from this, we're going to record this. So, and the important things to record are your interval, 4.814 to 2.814, and we get a more precise interval because we had a more precise degrees of freedom, and the degrees of freedom our calculator gives us is 13.145. So we would want to record both of those. Our conclusion is that we are 99% confident that the interval from -4.8 to 2.8 captures the true difference in the mean number of chips in Chocolate Chips Ahoy and Great Value cookies. So the question is, does your interval provide convincing evidence, that there is a difference in the mean number of chocolate chip cookies? And the answer here would be no, right? Because 0 is a plausible value in the interval. Okay, so that's our confidence interval for a difference between two population means.